2023. I think most of you are familiar with Friends of Lake Monroe, but we are a nonprofit that's focused on protecting and enhancing Lake Monroe. And we look at the lake, but we also look beyond the lake at its watershed. You can see on this map here, there's about 440 square miles that drain into the lake. And so anything that's on the ground has the potential to get washed into the lake when it rains. And that's one of the ways we can think about protecting water quality, is thinking about what can we keep out of the lake. We put together a watershed management plan that we published last January, and that identified the top 3 water quality threats as sediment, nutrients, and fecal contamination. And sediment and nutrients in particular can lead to those harmful algal blooms, which really complicate drinking water treatment. They can make it unsafe for recreation, and the best way to avoid them is to keep nutrient levels at a minimum in the lake, so keep the sediment and the nutrients out. Last year, we did a lot of forums talking about the watershed management plan. We talked with a lot of different organizations that work with the lake, trying to get everyone informed about what we want to do, because that plan also lays out next steps for improving water quality. We did a program educating about septic system maintenance. Failing septic systems are another potential source of nutrients and fecal contamination. And we had a voucher program where we would reimburse people for pumping their tanks. This year we have a new cost share program that's more geared towards farmers, helping to pay for soil and water conservation practices. So examples might be planting trees and native vegetation along streams to act as a filter, or putting up fencing so animals can't get into streams, using cover crops in the winter to protect the soil after the main crop has been harvested. So we have funding available for those. If you know anyone who lives in the watershed who might be interested, please send them to me. And then we're continuing to do our general education and outreach, hosting meetings like this one. We have some upcoming kayak trips and hikes, and we're gearing up for a big Lake Monroe Day celebration this fall on September 17th. But tonight, we've invited Dr. Eric Barefoot to come and speak. He is a researcher at IU, and he's going to talk a little bit about sediment movement. And we're really curious about this because trying to quantify how much sediment is getting into Lake Monroe from stream bank erosion and lakeshore erosion gets very tricky. But there's some really interesting techniques that he'll talk about that can help try and quantify some of these things or get an idea of how the sediment is moving using aerial photographs and a variety of other techniques. So with that, I'll hand it over. Thanks for being here tonight.
Yeah, thanks for asking me to come out. So yeah, I'm just gonna sort of give a broad survey of the kinds of things we do and the kind of tools we use to do river research science of all kinds, mostly, like Maggie said, tracking sediment, because sediment from rivers is what builds the landscapes that we live on. And the hill slopes that we live on that are above the rivers contribute all their sediment to the rivers eventually. So understanding how sediment moves around is a really big importance to understanding the health of watersheds and lakes that we live near and that we drink out of. So there's a couple other reasons though. It's not just sediment. There's lots of reasons to study rivers in particular. For instance, the vast majority of the world's population, something like 75%, live within a certain radius of a river. Yeah, is that possible? There are a couple pictures that would benefit from having less glare.
Yeah, it's great.
Keep going.
Oh, keep going. Oh. Yeah, perfect. Nice. So this is just
down on that one.
This is just London, London in the UK. So this is the Thames River, which flows down into the ocean here. And so this is the city of London, a megalopolis of hundreds of thousands of millions of people, and all of them share this water and live on the banks of this river as sea level continues to rise. The entire city is situated something less than 100 vertical meters from sea level. So as it starts to rise, cities like this that are on the coasts are really in a lot of danger. But also rivers are incredibly important for commerce. Something like, I think, something like 40% of all of the goods are transported on rivers as opposed to rail or other pathways. Don't quote me on that number, I can't remember exactly what it is, but rivers like the Mississippi River here, this is the delta of the Mississippi River. So the Mississippi flows and drains water from about 12% of the continental United States or the continental North America and funnels all of it and all of that sediment down here to Louisiana, where the delta spills, or the river spills out into the Gulf of Mexico. And that sediment that's moving along is what builds this landform that I'm showing you here. So this is sort of tens of kilometers. You can think of it as like 6 or so miles. But this channel right here, this is called Southwest Pass. This is the port for which every boat that wants to go up and every piece of commercial goods that wants to go up the Mississippi has to enter the United States of America through here and be piloted up the river, up the Mississippi River. And the pilots earn something on the order of $400,000 a year to live right here and drive out and pick these boats up and drive them in. And it's an incredibly lucrative job because the riverbed is constantly changing. It's being dredged, but also sediment is moving along the bed of the river, causing bars to pile up on one side or the other. So the pilots are always learning a new route. So the rivers are incredibly dynamic, and they were super important for commerce. But as they change over time, they're also really responsive to climate change, for example, or really big storm events. So I lived in Houston, Texas for 5 years while I did my PhD. And I was there in August of 2017 when Hurricane Harvey dumped about 5 feet of rain. Or I'm sorry, 5 feet of rain in 48 hours, flooding all the bayous. So this is Buffalo Bayou in Houston, Texas. And so all of this water had to go somewhere, but it just didn't have enough time. So it just filled up these channels. And so the entire city of Houston, I was volunteering, helping people knock out houses for weeks after this. I think most of the city was doing so. I was lucky I lived on a ridge, but rivers, when they break their banks, for example, this is an example of a river flood, as opposed to, so Hurricane Harvey was all this rain falling directly on the city of Houston. But when rain falls in other parts of the catchment, like in Lake Monroe, it flows downhill and accumulates. So the further you are downstream, the more water is pooling in one location. So you can get floods near your house, even when there's no rain, simply because there's rain somewhere upstream that causes the river to rise. And so this is an example from, I believe it's the Missouri River, and this is in Arkansas. And so this is a man-made levee here. So this is actually a structure. This structure was built to contain floodwaters, but obviously didn't do quite a good enough job. And what's kind of crazy about it is that actually the water here is mostly, we have these incredibly high velocity flows. This water is probably moving somewhere on the order of 10 kilometers an hour, or like maybe like almost a couple miles an hour. And that's a lot of force scouring on the bed of the channel here. So they're really destructive, and there's lots of energy that's moving around. But even though floods are destructive, floods are also really essential. This is a picture of the River Nile, and I think a lot of people are familiar with the story of how this little strip of green came to be. So this is the Sahara Desert, and the River Nile flows from Lake Victoria up and until eventually goes into the Mediterranean. But this little strip of green agriculture is sustained in part because of the water, but also in part because every time the river floods, it lifts that sediment that it's pulling down from sub-Saharan Africa, and it sort of spreads it across the floodplain. And that makes for rich, fertile soils and farmland. So this agriculture here is entirely dependent on rivers flooding on periodically, even though those floods are really destructive. So in the short term, we have sort of floods are bad because they can inundate crops, wash away houses, but in the long term, they are actually really essential for maintaining landscapes and keeping farmlands fertile. But rivers are also super dynamic. They don't just stay in one place. So here's a series of images from a satellite that's orbiting Earth. So there's this, USGS has been running a program called Landsat, which has been flying and essentially acquiring images of Earth every 16 days in the same location since 1984. So we have a lot of images. And so we're skipping over some in here simply because, for example, when there are clouds, you can't see. So this is a village in Peru. It's just to the east of the Andes Mountains. And so this river is flowing from the bottom to the top of the page. This is one of the major tributaries of the Amazon. And as you can see, over the sort of 30 to 40 years that these photographs encompass, the river has not stayed in one place for much of very long, and this town has had to grow and become larger while it's living next to an incredibly dynamic landform. That's, let me see if I can get you a better sense of scale. This river is probably almost 2 football fields wide, and it's moving super fast. Yeah.
Your time lapse is also showing the deforestation upslope from the river.
Oh, 100%. There's a beautiful time lapse, as you can also see of, you can see people cutting and burning. Yeah, 100%. So there's a lot of that going on here as well. Thank you for the observation. That's super sharp.
I lived in Peru and I've been to Pucallpa. So
Oh, have you? Oh, right on.
Brazilians don't like to hear it, but that is the Amazon River.
Yeah, it's part of it. This flows directly into the state of Amazonas later on, so further downstream. But yeah, so these rivers, and as they move around, they leave behind landforms. So you might notice that when this river bend here, so we call these meandering rivers, that is that they meander, but they sort of wiggle and are sinuous, but they also move through time. And so as they move, you can see that this bend in the river got cut off, and now it has formed what we call an oxbow lake. So it's sort of like a bow shape, and so this bow-shaped lake right here is the remnants of that old meander bend after it's been abandoned. And eventually these do fill with sediment, but it takes time. But there's this inherited topography from all the dynamic things that are happening in rivers over time. And so what are some of the ways that we can mitigate these sort of less desirable outcomes, but also preserve some of the more desirable outcomes? There's a lot of infrastructure that we've built in the United States and across most of the developed world to try and mitigate these impacts. And they include sort of mega projects like the Hoover Dam, as well as other huge projects like building levees, earthen levees, artificial ones to hold in floodwaters across most of the Mississippi River. So this incredibly large, this huge amount of infrastructure includes a lot of dams and a lot of other things. And so, for example, here's a map showing a point for every dam in the United States of America. So there's quite a few down here, even in these really slow sloping areas. So Mississippi has quite a few. There's a lot on the East Coast. A lot of these are old mill dams, for example. And then there's a few of them out west, and there's a lot in Los Angeles. But all of these dams are actually, I think it's something like 60% of them are privately owned, which is interesting. So they're not public utilities, they're actually privately owned, as was this one. So this is, if y'all remember, in Michigan, the Edenville and Sanford dams are just upstream of the town of Midland. And during a huge storm, I think it was like a 500-year storm, the dam failed as the reservoir got too high. And then eventually the water was able to breach the dam, rush downstream, and the resulting flood wave forced the evacuation of the entire city of Midland, because this flood wave went downstream into the next reservoir downstream and caused it to fail as well. So there actually was a cascade of dam failures caused by this single landslide. And part of the reason for this failure was actually the private ownership and scuffles in management practices between the state and the private owner. And so the policy decisions around what we do with public infrastructure can have really big consequences. I think that's probably preaching to the choir here. But the question is, how do we, as we move into the future, what the central sort of theme of the research that I do and the research that our group does at IU is to understand how rivers are going to change through time as we move into a new climate reality. And so we use a variety of tools to answer these questions. And so I'll walk through a couple different things we do. Some of them involve satellites, like I was showing you the images. We also use aircraft, even humble ones like the one I have on the table here, and then a variety of instruments that we install by hand. So I'll just give you a sort of overview of the main tools. So the main thing that we're interested in is understanding how sediment moves. And sediment, when it builds topography, when it makes the landscape, it changes the shape of the landscape. And so one of our main tools is simply designed to measure the shape of the landscape. And the way it works is if you have an aircraft like this one in this cartoon, As you fly along, you can shoot lasers down to the ground. And then as you shoot the lasers down to the ground, you can measure how long it takes for that laser pulse to come back. And if you do this hundreds of thousands of times per second, you can get a really detailed map of the surface below you, both as it hits trees. So for example, it can bounce off, this is showing sort of in a cartoon way, that it can bounce off of trees along the way. And so you can actually get multiple echoes of that laser as it goes along. And so you can measure both the ground and then the height of the trees that are sitting over it. And you can get a three-dimensional surface this way. So this is called light detection and ranging, which is where the word LiDAR comes from. And so we do this a couple different ways. Like I said, we have aircraft, but I'll talk first about satellites. So NASA in 2018 sent a satellite up into orbit, and so it orbits over the poles. So you can see it sort of goes like this, and as it's orbiting around the Earth, it's doing this all the time, and so it's measuring, but only in one location. So it's essentially a distance, a rangefinder. And so as it flies over the Earth's surface, you can actually see it's measuring, this is an animation obviously, but it's measuring the elevation of every point below it as it goes along. And this laser, this space laser called ISAT-2, because it's primarily designed to measure the thickness of the ice caps. So that's what its main purpose was. But as it flies along and it makes all these measurements, it can actually collect so many that if you were flying it along a football field, you would actually get a single measurement of elevation between every single yard line. It's an incredibly precise instrument. So we have an incredible density of data. And so as you can see, there's a lot more of these crisscrossing green lines when we're here at the poles. But even as we get to the mid-latitudes and around the equator, we're actually collecting a huge amount of data there as well. And so one of the things we can do with this is, so this is not my work. This is from a student at IU named Jake Giron. He's a PhD student working in our group. And what he has done is he's interested in how we can use this satellite data to measure the levees on rivers, and how we can use this satellite data to measure how essentially steep rivers are, or how sensitive they are to failure. And so what you're actually looking at here is a plot from X. On the x-axis here is the distance along that laser line. So as the satellite is moving along, this is the distance in meters along that track. And then on the y-axis is a scatter of points, and all those points give you the elevation of an individual laser echo. So we're measuring, and you can see there's quite a lot of scatter here. So what is this? This is almost 6 feet of, this is almost, no, it's almost 3 or 4 feet of variability. So there's a little bit of noise in the data, but what you can see is that there's actually, as here, we're going over a lake. And then as we go up here, we're going over the sides of a river. So this is the levee of a river right here. And then here's the river channel. And then there's the other side of the river. And then we're back into the lake. And then here's a hill, and there's a sort of another hill next to it. So we're going to be able to measure with incredible precision from space the shape of rivers. So this is one of the main tools that we use. But we don't just do LiDAR with satellites. We actually have a drone. So this is the one I use to acquire and test flights out and get some overhead photographs. But we also fly this thing. So this thing is, we have a couple different names for it, but I like Mama Bird. Anyway, it's about this tall off of the table, and it's about this wide around, and it can carry up to 15 pounds of weight. And so that's what this instrument here on the bottom is. This is that LiDAR sensor. So we can measure, with this instrument, we can gather hundreds of thousands of measurements of the surface underneath us as we fly the drone around. And I'll show you what some of the benefits of this are here in a second, but we'll just give you a sense of what the resolution of that data looks like, or what the sort of measurements look like. So this is a picture of the cloud of points. So essentially all those different returns that we get from flying the drone. And right here, this is a bridge. This is actually just downstream of that dam in Michigan. because our group was doing a project looking at that. And what you can see is that these are the individual piers of the bridge as it goes across, and here's the river. And then I'll give you a side view here. And what you can actually see is that all these points, you can actually pick out individual power lines, for example. We get echoes from the power lines. And then we can see underneath the bridge, and we can see through all of this vegetation here. So that we can get both a map of the ground, but we can also see the actual structure of trees using this instrument. And so I'll show you what the benefit of using this particular instrument is. And the benefit comes when you're trying to measure something, measure these really subtle river features that you might be of interest if you're trying to measure how much sediment is moving around the landscape. So for example, this is a river bend of the White River, just to the, I think it's just around Worthington, Indiana. So it's not too far downstream from Worthington and Spencer. And so the river here goes along a little bend. So this is a big meander bend. And this river bend has actually been migrating 18 feet a year. So it moves in this direction. So it's been moving in that direction 18 feet a year. So the farmer who lives here and farms this land is not very happy about it. And the person who owns this land is pretty happy about it. And so one of our students has been interested in following what are the processes that are going on as this river eats away at arable farmland. And so one of the tools you might think to do is look at satellite data. And so if we look at this is an example of satellite-derived topography. So the earth tones and the pale whites are higher topography. The dark greens are lower topography. And so you can see it's pretty coarse. This is 100 feet per, each pixel is 100 feet on a side. And so the U.S. Geological Survey made another data set called the National Elevation Data Set with pixels that are 30 feet on a side. And that's what this looks like. So you can see now there's actually a river. So that's kind of cool. So here's what we call the cut bank. So this is the cut bank of the river where the river is cutting away at the sediment. And this is called the point bar. So it's sort of pointy shaped, I guess. And so you can kind of see now that there is a river in this data set. And then this is a data set from the state of Indiana. So the state of Indiana took an airplane and flew LiDAR across the entire state, and we can actually see a lot more detail, right? So for example, you can see here that whereas on this point bar here, you would think, okay, maybe there's some ridges or something. Maybe there's a few spaced ridges as you go back in time. Well, we can actually pick those out really precisely here. So you can see this is that part of the bar that's exposed as sand. And it sort of starts at low elevation and grades up to higher elevations. And you can see these spaced bar deposits. So these are individual ridges that are left behind as the point bar grows. So as this river bend cuts in here, this point bar grows with it so that the river actually moves through time. And so what you're seeing is the preserved surfaces of that bar as the river migrates. And we can actually we can fly the drone again. And so I'm showing you the drone data here. So you can see there's maybe a little bit more detail, but maybe not that much more detail. Who knows? So let's just like zoom in a little bit and I can show you how important having this drone data is. So if I blow those images up, this is the data set from the state of Indiana. So once again, right, we can see these ridges here that show the movement of the bar through time. So as it grows, these are essentially growth rings. And if we use our drone-based data, you can see an incredible amount more detail. So again, using the same sort of color scale, not only can we see the growth rings of the bar through time, we can actually see that there's a little bit of a river, or essentially a river channel, that gets scoured out during big floods right here. So this is a river that's getting scoured out. And you can see here that these are actually dunes. These are sand dunes on the end of the bar. And these are being activated whenever the river floods. So as the river floods, the sand is picked up and moved along, and it builds these dunes here. So essentially, this is one of the ways we can measure the amount of transport that's happening, is we can look at the size of these dunes. And we can also see, for example, that there are, let me see if I can find one. Oh yeah, here we go. Here's a couple. So these are drag marks of trees. So what we can actually see is that during really big floods, logs get lifted by the water and dragged across the surface. We can actually see those in the topography. And what's cool is that all of this works even though there's trees. So we can actually see below the trees. And if we go slightly further upstream, for example, now here you can see that the riverbank over there has a breach in it. So the river is on this side, and there's actually whatever riverbank there is, there's actually a cut. And as the water flows over in big floods, it doesn't just flow down the river, it actually flows across the bar through all of these channels and eventually takes sediment from over here and piles it up over here. So perhaps someday in the future, this river will no longer take the bend, but will instead take the shortcut, and the river will move entirely to a new location. So I didn't do any of this work either. This is actually a student in our group named Harrison Martin, who is defending his dissertation on the 3rd of May. So if you would like, they are open to the public, and you're welcome to come to IU and watch Harrison talk about this in much more detail. He's a really good speaker, and I'm sure he would be thrilled to have folks out. I can give you the details if you like. And so now I'll sort of orient you to a site I've been working at for the last couple months. So here we are at the library. The geology building is right here. And this is a field site, so Lake Monroe is sort of just to the south of us, but we're gonna focus in on this little fortune cookie shaped thing over here, this little bend in the river. And I'll tell you a little bit more about why. The reason is because as you get closer and closer to Lake Monroe, when river water comes from all of the watershed and starts to flow down, this is the place where essentially most of the water has now accumulated. And as it starts to flow into the lake, the water has to slow down because it can't just sort of, the water surface has to approach the lake level, so the water has to slow down. And so this stretch of the river floods pretty reliably. For that reason, actually, the Army Corps of Engineers purchased most of that land upstream of the river and leases it to farmers instead of allowing it to remain as private land ownership. And this is, of course, I think a little bit of a contentious issue, but what it means is that this land is essentially reliably floods. And we're interested in understanding, as it floods, where does the sediment go? And how can we imagine better places or better ways to keep that sediment from going into the lake, but rather keep it on the floodplains? So here's an aerial image of that little bend. So if any of you know this area, this is State Road 46. This is called Kent Road right here. And this is the place where you check in if you're a hunter and you need to have your deer tags checked. And if you're going out hunting in the fall, or I guess turkey season's coming up. Or is it already happened? I can't remember. Regardless, this is where hunters check in on DNR property. So this is managed by DNR. And the creek here, so this is North Fork Salt Creek, and it flows right through here. It actually goes around and comes over through here, and then goes this way. And the flow is from this side, around the bend, to this side. And so now I'll show you, so we flew the drone, we got some LiDAR for this area. And so I'll show you a map of what the ground looks like. And we'll zoom into a couple places to show you a little bit more detail. But as you can see, right, so this is the river, or this is the stream. And here's the road. And I've clipped away the bridge so that it doesn't interfere. But you can see, and so then here's the hills that surround. So the river's cut into a valley, and this is its floodplain. So it's farmed, and certain portions are farmed, and certain portions are forested. And you can actually kind of pick out the edge of where the plow goes to form this riparian zone. And so let's sort of look in a couple different places. We'll start, I think, right here. And this whole area floods, by the way, and I'll show you some pictures from a recent event. So right there, right? Yeah, so right about there. This is one of the fields just upstream. And so you can kind of pick a little bit of stuff from this. This is just Google Earth imagery, right? So if I show you the data that we acquired, it's pretty cool. not only can you see the field, but we can actually see the tracks of where somebody drove out to go around this power line right here and then drive back in. So we can actually see people driving across the field, which is kind of cool. We can see all these little hills, all these little bumps. And then some of these are actually pieces, the grass has been flattened by floods. So I'll show you another picture of that here in a second. We can use that to find the directions of how water was flowing in the past. It's sort of like a forensic piece of evidence. So here's a bend in the river. And again, we're looking at it through the trees here. But if we look at it and zoom in a little bit more, you can actually see that every time the river floods, or every time the stream floods, what's actually happening is that you get stand up here so I can point. The water doesn't just stay in the channel and flood uniformly. It doesn't sort of just fill up like a bathtub. It actually flows out through these little channels here that cut outside of the river. And so these little outlets, these little sort of release valves, are what's or sort of where water focuses itself and how it concentrates as it moves across. And so a lot of these are likely candidates for really intense soil erosion because the water is focusing all of its energy into eroding the sediment of that one place. But likewise, what it also means is that as the water starts to expand, so when it leaves the tip of this channel right here, or the tip of this channel right here, it's carrying all this sediment, and now the water has to slow down. And so as a result, the sediment will actually deposit. And so we expect that at the tips of the channels, we're hoping to find deposition over time. So that's a place where sediment essentially gets moved from one spot on the floodplain and deposited on another. And then, of course, in some places, water and sediment come back into the channel and essentially drain water and sediment from the floodplain into the river. So it's a sort of a lot of give and take of sediment that's moving back and forth from the floodplain to the river, from the floodplain to the river, each way. So let's look at another example of that. And I can actually, so this is another portion of the river, but what you can see is once again, there's these sort of offshoot channels. And so maybe one day Salt Creek will flow through one of these instead of its current path, but at the moment it doesn't look very likely. But what we can see is that actually in this field here, the grass is being laid down by these floods. So the water comes out of the river, flows across the surface, and then flattens all of the crops on its way down. So we can actually track that, and in the future, hopefully, let's see if I can actually get a picture of that. Oh no. Yeah, actually you can see it. You can actually sort of see a little bit of a fabric here. I'm not sure if it's tell, but the water is pushing the grass down in this direction. So we're hoping to use this as a way to track how the sediment is moving out of the channel and into this essentially a low spots, right? So the darker colors here are lower topography, and the sort of brighter colors are higher topography. So this low spot in the field both accumulates water, but maybe eventually will become a sink or a sort of holding zone for sediment. And so those are sort of our remote sensing techniques. So we use a lot of aerial craft and we use a lot of satellite data, but we also do measurements on the ground. And so this is work I've been done with my colleague at the University of Minnesota. His name's Andy Wickert. And he designs and builds his own instruments. So I have a couple examples right here. This is a data logger. So this is just essentially a custom-made piece of electronics to record data from instruments. And here's an example of one of those instruments that we might use. These little binoculars are actually a laser. And so what we can do is we can strap it like this. So for example, that's the instrument here. This is it deployed in Patagonia. And what you can do is you can attach it and have it look downwards at a point in the ground. And it just measures the distance however many times you want. And so this little laser rangefinder is very power efficient, and so we can actually deploy it in the field with AA batteries for up to a year. And it's also quite affordable. This data logger itself is on the order of maybe $100, $200. This thing's maybe on the order of closer to $500, but they're way less expensive than comparable commercial technologies that you might find. And you can actually build them yourself. All the code and designs are available on the web for free. So if you wanted, you could, but you'd have to build it. But we can use these kinds of things to build all kinds of stuff, like a weather station here that was deployed in Patagonia. This is just a diagram showing one of the sort of devices. It's just a water level logger. There's the data logger, and then here's an example of an instrument that's actually measuring the surface of a glacier. So this is deployed on the surface of a glacier, and this is a little echo sounder. So it's an ultrasonic echoer that's sending out a pulse of sound and measuring the return. And so it's measuring the surface or the distance from here to the snow. And over the summer, as the snow starts to melt and then also evaporate, glaciers, essentially the snow will start to move, and then this stake, the sort of ablation stake is what we call it, will record as the water, as essentially the surface of the snow melts away. So this is one of the sort of things we can do. And so we have a couple of these sorts of sensors deployed out here in Salt Creek. And so in addition to this topography, so we acquired this image, or this map here in early March of this year. And as you know, we've had quite a few floods already since then. And we're going to have probably quite a few more next spring. And so we're planning to go back a year from now and do another flight and measure the change from one year to the next. But in the meantime, on the floodplain, at every single one of these white dots, I have installed this. So what is this? This is essentially a fence post from Menards, much like any other one you might buy. And then tucked in here is a self-contained kind of water level logger. So what it does is essentially all it does is measure pressure. So at the current moment where it's sitting on the surface, it's actually just measuring the air pressure. But when it gets covered up by water, the water exerts more pressure on the sensor, and you can measure the depth of the water by measuring the pressure that's being pushed onto the diagram. And so we have 20 of these deployed across the area. And so what we're planning on doing is during events like this last one we had here in April. So this is looking out from, I'll point out where this image is from. So this image is taken right here, looking in this direction. So we're looking downstream over the channel. And you can actually see, so there's a lot of water. So this was when we had something like 3 inches of rain in one weekend. It's a lot of water. And so we're standing and looking downstream, and you can see that the creek here is definitely over its banks. And then there's quite a bit of water flowing this way across the floodplain and across the riverbanks into this open field right here. So this is where that little channel is. This is where this field is. And so the water is flowing outwards and taking sediment with it as it goes. And so what we have is we're able to measure the water level, or essentially how deep the water is, at every point where there's a white dot. And what we should be able to do as a result of that is actually make a map of the water inundation that sort of flooded this entire area, and then come up with an estimate of how fast the water was flowing and how much erosion and deposition and sediment movement we could have expected during this event. And then we can compare it to our flights from the drone. So we can also do that. We can then verify that a lot of this stuff by looking at the dirt itself. And so one of the ways we do that is by drilling. So we'll actually do really shallow drilling. So what we'll do is we'll take, for example, this is in a lake here. This is a sort of a soil auger, but much like you might do to drill a well or to do a soil test. So this is just essentially a long pole and then a bit that you screw into the ground by hand. So it's really hard work. We can take one step up and we can use this amazing apparatus here where you use an aluminum irrigation pipe and a concrete vibrator. And so the concrete vibrator shakes the aluminum pipe. And as we shake the aluminum pipe and it sits on the soil or onto the wet saturated sediments, every time as it jiggles around, it sort of jostles every sand grain left or right. And as a result, what it does is it right around the edge, right around the barrel of the aluminum tube, it liquefies the sediment, and you can push the barrel into the ground with almost no resistance. So this is a technique for getting cores, or essentially drilling in saturated sediments or water saturated sediments. And so we can do this in lakes so this is an example from Minnesota where we've been out on a frozen lake and we drilled a hole in the ice and then we drilled into the lake bottom. So it means we didn't have to have a boat, which is kind of cool. And this is an example from a floodplain also in Minnesota. But what we can do is that with this sort of thing is we can push the aluminum barrel sort of 10 or 15 feet down into the ground, and then we turn off the concrete vibrator, and so that causes the sediment to stop liquefying. It freezes in place, and then we can haul that sediment back out, cut open the aluminum barrel, and look and see what it looks like on the inside. So it's like punching a straw down into your parfait. And so with that, I'll let this little loop play again. You can just watch this as it goes, and I'm happy to take any questions about the kind of stuff we do.
Have you run your drone over Lake Monroe and used it around the boundaries of Lake Monroe?
You mean like on the shoreline?
Yeah.
No, we haven't done that yet.
Something to think about.
Yeah, something to think about for sure. Yeah.
So if I'm understanding right, the thing is, I guess I was assuming that sediment got into the river more or less by rain falling on dry land and then going downhill into the river and carrying sediment, particles with it.
Mm-hmm.
And I assume that does happen, but what you were showing us was during flood episodes, that so-called dry land no longer being dry.
Mm-hmm.
And the river becoming, in a sense, very wide, but shallow and sort of sweeping across what used to be dry land,
Mm-hmm.
taking a shortcut, and presumably picking up a lot of particles and ending up a little further downstream in the regular river bed.
Yeah.
So is that a more important source, do we know, of sediment entering the flow and eventually getting as far as Lake Monroe than the old concept I had in mind?
Yes, there's other things that are happening too, as well. So I think I like to think about it, and I think a good way to think about rivers is not as funnels, but as sort of like not as a funnel, but as more like a funnel cake, I guess. I don't know. It's places where it can. I'm trying to think about a good example of something where it sort of flows back and forth between different areas. So sediment doesn't just sort of flow down into the river, like you say, and go. It actually, so there's enough area here where anytime it floods, sediment can get picked up. And since the water is moving so much slower out here than it is in the river, essentially, the slower the water goes, the less sediment it can carry with it. And so if you slow the water down, that sediment starts to settle out and lands on the bed. And so all of this flat land was built by the river flooding and depositing new sediment next to it. So with all of these fields here were actually built by the sediment leaving the channel, leaving the river and landing next to it, essentially. So it's more like it's borrowing. And so over a long period of time, some of that sediment, like you're describing, that gets picked up and moved along will get deposited here. But also sometimes some of it will get picked up and carried back into the river. And a good example of this is, the river's moving along. And so this river is moving much like others, just a little bit more slowly. And you can see right here, so this is one of these this little cusp right here, or this little cusp right here, or even this one right here. This one's probably the best example. So this is the riverbank. But then right here, you can see that there's like a cut taken out of it, like a cookie slice or like a bite. This little thing is essentially a small landslide. And so what happens is that the riverbank failed, part of it slumped into the river. Now that's new available sediment in the river to get moved downstream.
So in other words, in this area, there might be no rain falling in this area.
Right.
But because of water coming from upstream, pulsing out into the floodplain and then withdrawing and pulsing out, or washing across a peninsula, you can have a lot of sediment either deposited or picked up and taken downstream without rain falling on this area.
Exactly. Right. 100%.
Have you ever looked at the particle size going in versus coming out?
Oh, like the grain size that comes, yeah, so the particle sizes that are leaving the floodplain. And yeah, so typically these ones are very fine. So it's like silt or clay. And then actually most of the sediment moving in this river is really fine grained. Only in the bed do you get like sand. So there's a little bit of sand down there, so that's coarser material. But so yeah, so when I say sand, I mean those are grains or particle size classifications. So sand is anything from 2 millimeter or 2 mic. No, it's sand is anything from 2 millimeters down to about 4 microns. So it's sort of the sand or silt is that range, and clay-sized particles are usually the finest things, and those are 2 microns or finer. So yeah, I thought you had a question for I want to make sure you have to.
More questions. So I think it would be really great if you could talk to NDOT about this specific project.
Okay.
Because I heard they may be doing some improvements to State Road 46, and this would be a great area for their highway to look at.
Yeah, they actually did.
You're not far away.
They actually built a new bridge. You can see it in the Google image.
Mhm.
There's a new bridge right there.
Yeah.
Years ago.
That was it.
Yeah, a couple years ago. Yeah.
I don't think they're doing improvements under design right now.
Are they looking to lift the road?
I can't say for sure because I don't want to misspeak in a public meeting like this,
Sure.
but in design for construction in the next couple of years.
Cool.
Or maybe
Yes.
they will.
Sorry, I'm not sure who was first, but I'll go.
Yeah.
We'll go left to right.
So, you talked about water leaving the confines of the Salt Creek, going out into the floodplain and sediment being deposited there. That only happens during high water events. Most of the time, the water stays within the confines of the creek and the sediment's being transported downstream into the lake.
Mhm.
So, do we know at all, is there any kind of comparison? I mean, is what's actually deposited into the floodplain a small part of what goes down and ends up in the lake? Do you know at all? Can that be quantified?
Yeah, it can be quantified. We haven't done it specifically for this location, but a general rule. Yeah, it's a great question. There's a general rule kind of comes that the really big floods move a lot of sediment, and then most of the time, if I were to show you a picture of this from only a couple weeks earlier, the river level is almost 10 feet lower, and there's not much moving, and it's pretty slow. And so most of the time it's like that, but the thing is the river's moving very slow, and so it doesn't get to transport very much sediment. And then there's of course sort of a sweet middle ground where it happens enough that there's enough force to move sediment. And so there's a lovely paper, I think from like 1964, where they make the analogy of a dwarf, a man, and a giant chopping down trees. And the giant sleeps most of the time, but he knocks down a huge amount of trees when he does get to work. And then the dwarf is working all the time, but has to work really hard to chop down a single tree. And then the man is sort of in the middle because he works 5 days a week and chops down enough trees to cut down most of the forest. And so as a general rule, it turns out that about sort of 1 to 2 year flood does most of the work in the landscape. So it's sort of it turns out that as the floods get larger, their ability to transport sediment increases as an exponential function, or sort of, it's not quite an exponential, but it's pretty close. It's more than linear. And so there's the way it works out about every year, whatever flood comes back about once in a year, moves the vast majority of the sediment, as it turns out. So yeah, that's a general rule of thumb.
So, could you talk about how different particle sizes react to the different floods, the dwarf, man, and giant?
Yeah, for sure. So when in a flood like this, you can actually, let's sort of see if I can think about it this way. So if you were to look at if I were to sort of magically take a column of water, a cylinder of water, and just lift it out of the river by magic, and then look at it, you would see that there was more sediment at the bottom than there is at the top. because as the water flows along, you can actually pick them out here. You can see how there's sort of little shapes here, and little shapes here, and little sort of what are essentially, there's sort of texture on the surface of the water. That texture on the surface of the water is turbulence, or sort of big eddies that are moving through the river, and they're sort of touching the surface. And so this water is boiling, almost like a pot. It's not boiling because it's hot, it's just turning over. And so that motion of the water, that sort of turbulence, is lifting up sediment along with it. And so the sediment's at the bottom of the river, and the river water picks it up as it spins around and sort of does this convection thing. And so the water picks it up, and so the sediment starts to get picked up with the water, but at the same time the river's picking it up, the sediment's actually settling back down again. And so if we were to take that column of water, and we were to see how the sediment was distributed within that column, the coarsest grains are on the bottom. And the reason for that is that they're the heaviest, and they fall. So they fall faster than the river can pick them back up again. But the clay and the silt, those really fine particles, they fall through the water really slowly. And so it's easy for the river to pick them up and suspend them in the column. So if you were to take a skim of water right here from the surface, it would be mostly silt and clay. And if you were to take a chunk of water from the bottom, it would be mostly sand. And so that's sort of the grain sizes get distributed that way vertically, so in a stretch like this. And so then, of course, the only stuff that's escaping from the river is the stuff that's on the very top. So you're just skimming off the surface. And so since you're skimming off the surface, you're only getting the finest grain sizes, those clays and silts. And so those end up ultimately what gets deposited on the floodplain. And so if you walk out into a place that's flooded like this, not too long after the flood, and you go and look at some of the vegetation, and you just touch the leaves, they've got that sort of fine silty clay coating all of the leaves, and that's what's getting lifted up and sort of distributed across.
So the sand has to travel within the course of the river.
Unless you have a really big flood.
Unless you have a really big flood.
And then sometimes you can pick it up. So there's a mathematical relation that describes, that can tell you what grain sizes you're going to get at every inch of the water column given a certain amount of flow. So, yes, I'm sorry, we should get to you.
I have a question about sediment load. I don't know if you're familiar with the watershed study.
Oh, yeah.
And there was a little bit of information in there about the sediment load, and I don't remember the figures, but so much sediment goes into the lake, and then lesser amount comes out.
Mm-hmm.
And I don't know what the implication is of how much is left per year.
How much comes out? Does any come out?
It's like 10%.
Oh, that's even surprising. It's that much.
Yeah.
I think what I heard was about 1/100 of an inch per year deposit in the main body of the lake.
I would
Not very
be.
much. That doesn't seem like very much.
Most of the deposit is up North Salt Creek, and Salt Creek where it just comes in.
So if we look at the map of, I wonder if I had a good enough version. Yeah, okay, we can see it. Okay, so here's where this field site is, here, and then here's the very tip of Lake Monroe. So this is where Salt Creek flows into Lake Monroe. Likewise, with the finest sediment, as the river flows down, or as the sediment comes down the river, the finest sediment can sort of drift out into the lake and sort of float really easily because it sinks so slowly. But most of the sediment is this sort of silt or sand, or some of it's sand, and then a lot of it is silt, which sinks a lot faster. And so that silt accumulates right in here. So this is actually a delta. So this is a river delta, much like the Mississippi Delta that I showed a picture of. It's just moving into a lake rather than into the Gulf of Mexico. And so this is the delta. So this is actually where most of the sediment is going to accumulate over time. So a large amount of it gets trapped here, and then the very finest grain sizes sort of can drift out into the lake here and start to settle in other places. But I'm surprised that even 10% of it makes out of the dam.
Well, maybe my numbers are off, but
No, it could be, but I don't know.
it was relatively small. Most of it, vast majority stays in the lake.
Yep, and I'm betting that most of it's accumulating in these deltas right here.
Are nutrients bound to the the sediment particles, like the silt and the clays, and are they more bound to the clays and the silt versus the sand-sized particles?
Yeah, if you look at a clay particle in a microscope, clay-sized particles usually are a kind of mineral. So once they break down to that size, it's a kind of, so for example, quartz sand doesn't often break down to clay-sized particles. Once you get to the size of like a sand grain, it becomes difficult to make it any smaller, actually, which is kind of surprising. But I'm happy to talk more about that. But the clay-sized particles you get are actually clay minerals most of the time, and what they are is sort of sheets. So if you look at them, have you all ever seen mica before? Yeah. Mica is this sort of sheets of material. Clay is like that, but much smaller particles. And so those little sheets actually are those are sheets of silica here, and then in between them are other ions, other big things like potassium ions or calcium ions that are stuck in between. And so then it's actually very easy for nutrients of various kinds to sort of get stuck in the crevices and get attracted to those particles. They tend to be sort of negatively charged. And so there's lots of things that can stick themselves to those clay particles. So they do tend to accumulate a lot more nutrients of all kinds of various things that you can imagine. They bind very tightly to lots of environmental contaminants. And so those are preferentially going with them. A quartz grain is big and kind of bulky, and so there's not a lot of sort of surface area for it to get stuck onto.
And so how do silt and clay particles compare nutrient-wise?
Oh, actually, I don't know. Silt particles are pretty small, so they probably have a fair bit as well. But I don't know exactly what the relative trapping potential is for those two things. You actually might know way more about that than I do.
Nope, not my area.
Yeah, I'll say one other word about Pucallpa, since Friends of Lake Monroe is interested in deforestation also. Pucallpa is there, basically it's a river station for the logging industry.
Oh, really?
Logs come down the river to the city, and if you were there on the bank of the, at Pucallpa, on the, I forget what the river's called there. Yeah, that's all just a big lumber yard.
Well,
Trump yard.
yeah, it's a pretty crazy place.
All right. One last question, Kelsey?
Or I could
Go ahead.
real quick. I'm really interested in the technology you're using.
Okay.
And I have interest in it because we have some sinking streams on the west side of Bloomington that haven't been studied since a PhD student in the geology department in the 70s.
Oh, right
And
on.
we're still doing our flood modeling based on their estimated rate that the sinkholes are draining. And things have changed a lot since then. And we just don't have up-to-date information on how fast those sinkholes drain. And we have people living in the floodplains and in the storage area when the sinkhole backs up. So I'm really interested in when they just finding out more about those sinkholes. So just kind of a plug if anyone interested in karst.
That's amazing.
Yeah.
Where is this?
On the west side of Bloomington. So we have about
okay.
Two large sinking streams. One drains about 3 square miles. The other drains almost 5 square miles.
Yeah.
I know this is like Monroe meeting, but still interesting. So
Yeah, that's interesting. Karst sort of makes everything more complicated because you don't have the river is not on the surface, it's also in the subsurface. So you have pipes to work with.
But
also.
exactly the technology you're using is, I mean, what I would love to have more data in that.
The state just recollected LiDAR in 2018.
Yeah.
So.
Is that down to 1 foot?
Yes, I think it is. It's close. It's pretty close.
But to have the surface water elevations as well during flood events.
Oh, yeah, sure.
Yeah, that's the information I would love to have.
Oh,
Try
yeah.
and,
So the instruments I was showing you, I mean, obviously it depends on budget, right? But like we had these lying around the department. They're just like we just accumulate them over time. People buy them, and then they're sort of. I mean, they're really handy to have, but they're on the order of like a couple $100. So they are not cheap, but they are also incredibly durable and was super useful. You could imagine finding there are other ways to do this more in a citizen science framework. For example, you could just install a bunch of fence posts with measurements on them and have people go out and look at them, for example. That's like a thing that, there's one of the lakes near my home, so I'm from North Carolina originally, and one of the lakes near our house has essentially a ruler and a QR code. And if you walk by and you want to take a picture of it and measure the lake level, go for it. And so they have data collection this way. Yeah.
All right. Well, thank you again, Aaron, for coming and speaking to us.
Thank you all for inviting me. I
Really
had some
Everybody's welcome to hang around, ask your questions or chat. I just want to say real quickly, we do have a hike coming up on May 9th to the south area.
You know,
We
which
have
one is
a
the right
kayak
order?
trip coming up on May 21st and a shoreline cleanup at Town on May 25th. We brought all of our standard literature if you guys want anything, and if you are not yet a member of Friends of Lake Monroe, I would encourage you to join. Membership is as little as $25 a year, and it helps support this work to protect our lake that we all love. So thanks for being here tonight.